Okay, I'm going to start reviewing limit definitions and continuity. Okay, so suppose I have this function f of x, and I want to show that it has a limit L as I approach the point x naught. Now, let's recall the definition of a limit. That says that if we have some small distance in the y direction, epsilon, I can find a corresponding small distance in the x direction, delta, so that if I'm within that delta window of x naught, then I'm definitely within an epsilon window of L. Okay, so let's go ahead and just look at this picture and see what that's going to mean. So if I look over to my function and draw these nice little lines from the y-axis and to the x-axis, I just have to pick the smallest of these two distances, right, to guarantee that I'm going to be within my epsilon window of L. So let's name this smaller distance delta and simulate it on the other side. Okay, so if we go up here, when I go back over, I've shown that my function value within delta of x naught on either side is within epsilon of L. Let's write that down formally. Okay, the formal definition for the limit says that the limit as our x values approach our x naught value of the function f of x is equal to L if for every small value in the y direction, epsilon, that's bigger than 0, there is a corresponding small distance in the x direction, delta, bigger than 0, so that if we're within delta of x naught, then our function is within epsilon of L. Okay, now that we have our formal definition of the limit, let's talk about what it means for a function to be continuous. So you guys are obviously old hats at this by now, and you know that a function like this, where we have a discontinuous point here, is not continuous. But why is that? We know just kind of inherently that a function is continuous if we can draw it without lifting our pen up, right? So I would want to have it like that. So I wouldn't have this point up here. So let's go ahead and write the definition that our function is continuous at the point x naught. The definition of a function being continuous says that our function f of x defined on the closed interval a to b is continuous at our point x naught, somewhere in between a and b, if the limit as our x values get really close to the point x naught of the function is that the value of the function at f of x naught. Now notice there's actually 3 things that have to be true for this to be true, and the continuity test describes all of them. Let's go ahead and write that down. The continuity test says that f of x is continuous at the point x naught if 1, f of x naught is defined, 2, the limit as we get close to that point x naught of the function exists, and finally they have to be the same thing. Okay, now let's talk about some different kinds of limits. So now imagine this is my x naught point. When the function is approaching x naught, it looks like it's going off to infinity, right? And notice we'll just be considering x approaching x naught from the positive side. But what does that mean, right? I can't really say that for some delta I'm within epsilon of infinity. What I'm saying is that I want to figure out what it means that the limit as x approaches x naught of f of x is equal to, and remember we're just going to be coming from the positive side, is infinity. But infinity is not really a number that I can deal with, right? I can't draw some line and say, oh, here's infinity, let's draw my epsilon window around it. That doesn't make sense. So this is not right. So what does that mean? I need some way to talk about infinity without dealing with the number infinity itself, because it's not a number. So instead of calling this infinity, what if we just call it, I don't know, maybe some big number b? So if I say that the limit is infinity, I'm saying for every big number b, I can find some points where my function goes above b. In other words, I can find a delta where if I get close enough, if I get within delta of my x naught value, then I'm going to be above b. My function has gone above b. Okay, let's write down that definition formally. Okay, the definition of my limit of my function as I approach my value x naught being infinity is true if for every big number b, there is a corresponding delta so that if we're within delta of x naught, if my x values are within delta of x naught, then my function values, excuse me, I don't want that, that line, then my function value is above b. And similarly, we can write down the definition for a negative infinity. Let's do that quickly. The limit as we approach x naught of f of x is negative infinity if for every, let's just say, big number that's negative, b is negative, notice less than 0, there is a corresponding delta so that if we're within delta of x naught, then my function is below b. It is even more negative than b. Okay, finally let's talk about how we can describe the behavior of this function as it goes off to infinity in the x direction with limits. So in this case, right, the problem isn't that we're trying to describe the limit, right? The limit is some finite number. We can tell it's getting close to this number L, but the problem is our x naught, right? We don't know, we can't just say, here's my x naught infinity, right? Just in the other case, that doesn't work. So we have to figure out some way to describe x going to infinity. So if I'm saying that the limit as x goes to infinity of f of x is L, what does that mean for my x? Okay, the definition of a limit as x goes to infinity says that the limit as x goes to infinity of f of x is some finite number L if for every epsilon bigger than 0, there is a corresponding, now this is the part that's different, right? This is where we're going to have to change because we can't use a delta. Instead, there's a corresponding m, big number bigger than 0, so that if x has gone past m, if we're farther than m towards infinity, then we're close to our L value. Our function is getting really close to its limit. Now notice this is kind of similar to the infinite limit case where we were talking about a b greater than 0, right? So in each case, b and m are these big numbers, and we are able to get close to some other value In this case, we're getting close to our L with epsilon. In the other case, we were getting close to x naught with our delta. Okay, finally to recap, let's just quickly draw pictures of all of our types of limits. So the first one, imagine that we're just, we have this finite number x naught, and we have a finite limit L. We know that the limit of this function is L if for every epsilon distance, we can find a corresponding delta distance, so that if we're within delta of x naught, then we're going to be within epsilon of L. Okay, so in this picture, right, epsilons are our small y distances, and our deltas are small x distances, okay? Okay, now what about this case, right, the one where the function is going off to infinity? We can't use an epsilon, right, because the function's going towards infinity. There's no finite number. I can put an epsilon window around. Instead, I use a big number b. Let's say this is my big number b. So I can say when I get within some very small distance delta of my x naught value, I'm going to be above my b value, right? If I come over here from my delta and I go up, this goes above b if we're within delta of x naught. Okay, now, finally, the last case. Over here, imagine we have the function is approaching this number L as it goes off to infinity, right? So our problem now is that we can't use small deltas and a finite x naught. Instead, we need to just pick some large number m and say that after we go past m in the x direction, we're within our epsilon value. Let's put the m where it belongs, right? If this is our epsilon, then our m is somewhere right about here, right? After we go past m, the function goes within epsilon of L. Okay, now as an exercise that you might want to try on your own, imagine this is our function f of x. It appears as x goes to infinity that the function also goes off to infinity. So can you figure out how to write the formal definition of the limit as x going to infinity of the function being infinity?